We will have a truss system as shown here. Okay, we have dimensions and going load at here. Okay, so here we have members made of these Douglas fir woods. Okay, you have a Young modulus of 1.9 10 power 6. Cross sectional area is 8-inch square. Uh, uh, so we are interested on calculating the average stress of each members. Okay, we have to find the internal force later on in each members. Okay, then we divide by A, probably we can get the stresses. Okay, but first we have to solve the displacement lah. So we want to find the displacement of each nodes. Okay, in of course global coordinates. So here we have so-called 1 member, 2 member, 3 member, 4 member, 5, 6. So I can say that I have 6 elements. Right? Then in terms of node, I have 1 node, 2 node, 3, 4, 5. So I have 5 nodes. So you are expecting each node I have x and y directions. Okay, x and y, x and y. So I am expecting we have a 5 times 2, 5 times 2. We have a 10 times 10 matrix. Okay, for the k global later on. Okay, so how we want to do it? So first we have to look into we group them first lah. So you can see that this is 3 feet. The height is 3 feet. Okay, the length is also 3 feet. Okay, so I would say that member number, what we call element number 1, number 3, and number 6 are having the same so-called K. We have K equals to AE over L, right? So K for elements, element 1, 3, and 6. So they are all in horizontals, okay? All laid down with theta, which is 0 degree. Okay, so that is its so-called, we can group them in one at the same. So K equals to AE over L, where your L equals to 3 feet or 36 inch. Okay, 3 times 12. We can look into the element number 4 also. Okay, element number 4, our K equals to also AE over L, and the length also the same. L is also 3 feet or 36 inch. So they are same. Just that the theta here is for element number 4 is 90 degree. Right. So that is one groups 136. Element number 4 is another groups of members. Then we have element number 2 and element number 5. Okay. So if you look into element number 2, element number 5 first. Element number 5, right? So the theta here, we have a theta and we have a different length. So this length is basically 3 feet, 3 square plus 3 square surds. Okay, this is its length. Theta here is because it's same, so it's 45 degree. Okay, so that is another group. Element number 2. So your theta here is from here to here. Okay, is 180 minus 45 is 135 degree. The length here is also the same, 3 square plus 3 square over 2. So total of them, we have 1 groups, okay, 2 groups, 3 groups, 4 groups of so-called K to be calculated. Okay, before we can assemble them. Okay, so that is just a summary. So now we discretize the problem into nodes and elements, 6 elements, 5 nodes. Okay, so if you look at this node 1 and 2 just now, so it will cover, the element 1 will cover node 1 and 2, right? Element 3 will cover node 3 and 4. Element 6 will cover node 4 and 5, right? Then element 4 itself is 2 and 4. Then element 5 is 2 and 5. Element 2 is 2 and 3. Right? So that it gives us the summary of this. right? Then the angle itself, theta is 0, 0, 0 for 136, and 4 is 90, then 2 is 135, 5 is 45. So that is just a summary of it. So we can find the stiffness, okay, for each element. Here you use this AE over L because you have a uniform A. A is a uniform, okay? So we don't need to use the average in this case. So we use AE over L. Then our A here is same for all the members. E are all same for each members, okay, because they are using the Douglas fir woods given 1.9 times 10 power 6. Then the length will be different for element number 2 and number 5. Okay, element number 2 and number 5, here you have 3 feet, 3 square plus 3 square, so you have 4.2426. Okay, this length is 4.2426 feet, or multiply with 12, you get 50.91 inch. Okay, so that give us the elements stiffness for the element number 2 and the 5 are same, which is 2.98 times 10 power 5. But element for 1, 3, 4, 6, because they are having the same length, then it's 4.22 10 power 5. Right? So that is the solutions for each elements, the stiffness. Right? Then we have the develop that equation out for each elements under the global stiffness matrix. So here, if you still remember our K under global is basically T K, okay, and T transpose. Okay, so that gives us this. Right, so we just substitute everything in. Okay, here we are looking into 4 groups, right? 1, 3, and 6. Element 1, element 3, and element 6 is having theta equal to 0. Okay, horizontal. Here, if you substitute everything theta equal to 0, then we have the so-called the stiffness matrix. It's basically similar like what you have seen in axially loaded members. Okay, U1x, U2x, okay, is 1, negative 1, negative 1, 1. Okay, Y have no displacement. Okay, so that basically gives us the first elements. But for element number 3, okay, it's covering node 3 and 4. So you also see that your node 3x and node 4x is actually having 1, negative 1, negative 1, 1. Right? Then element number 6, you have 4 and 5, also the same, 1, negative 1, negative 1, 1. Okay, so the transformations, or what we call the stiffness metric with this transformation matrix considered in, have helped us to consider the actual orientation already. So in this case, you know that when you lay down horizontally, okay, so you only have displacement along the x-axis. So you have only x-axis stiffness in this case. You don't have y-axis stiffness. But in the case of verticals, okay, so if you substitute 90 degree for the element here is number 4, covering node 2 and node 4. So you have 2x, 2y, 4x, 4y, and you substitute 90, then you will find out that your x is 0. Okay, x is 0. But y now is 1, negative 1, negative 1, 1. Okay, so it's similar like when you have axial members, okay, vertically, okay, loaded. Okay, so that gives us the stiffness matrix for element number 1, 3, 6, and 4. Right? Then we go towards element number 2. Element number 2 is covering node 2 and node 3 with the angle of 135 degree. So you substitute 135 degree into our stiffness matrix, elemental stiffness matrix, with the transformations matrix considered. So you'll find out that all of our displacement, we will have basically later on displacement, our stiffness will basically covering x and y. for both nodes. Okay, node X, node Y, node X, node Y for X direction, node 2 XY, node 3 XY. You will cover. Okay, then that will be giving us our stiffness matrix for element number 2, covering node 2 and node 3. Similarly, for node element number 5, covering node 2 and node 5, we also have this 2.98, basically covering X and Y for node 2 and node 5. All right. So we have all the elements, elemental stiffness for element 1 until element 5. 6. 1 to 6 elements. So now we can assemble them. Under pre-processing, if you still remember the basic computational step for FEM, you have built develop equations for one element, then you find the what we call the elemental stiffness matrix for each element. Then you have to assemble them. So now we have, if you still remember, it come back to here. Okay, we have node 1 and 2. Okay, the elemental stiffness matrix. 3 and 4, 4 and 5. So 2 and 4, 2 and 3, and 2 and 5, right? So what we need to do is we have to assemble them. Okay, so I redraw these nodes, so probably you can have a better, clearer view. Okay. So I have a node 1 at here, node 2 at here, 3 at here, 4 at here, 5 at here. Right? So of course node 1 will be using the what we call the global stiffness matrix for element number 1. Element number 1 covering 1 and 2, not 1 and 2, right? This is our element number 1. This is our element number 2, our element number 3, number 4, number 5, number 6, right? So if you look into that, basically, as I mentioned to you, we have 5 nodes. Okay, each node covers 2 directions, X and Y. So we have a total of our global stiffness matrix will be tens. Okay, tens times tens matrix. So this will be a tens times tens matrix. Okay. Then if you look into the first one, okay, just now we have obtained, if you look into node 1, our element number 1, it cover node 1 and node 2. So it's 4.22 in X only, positive, negative, negative, positive, K. Okay, 4.22. So in this case, you have this under X, Y, X, Y, right? So we are covering, this is so-called 1x, 1y, 2x, 2y, 3x, 3y, 4x, 4y, 5x, 5y. Okay, so same with here. This is 1x, 1y, 2x, 2y, 3x, 3y, 4x, 4y, 5x, 5y. All right, so it only cover the first element, or it cover node 1 and 2, okay, in X direction. So that give us positive K, negative K, positive K, and negative K. Negative K and positive K. Okay, so that gives us the first element. All right, so if you look into first element covering 2 nodes, okay, and it's cover what we call X only, okay, 1x and 2x. So that gives us this. So if you look into second nodes, or second element that covering second node itself. So beside this K1 itself, we also have K4, okay, covering 2x, covering 2y, okay, and 4y. We look into this 2y first, so it's 4.22. Then we also covering this negative. We have also this negative. Point 2.98 divided by 2 is 1.49 times 10 power of 5. 2y is a positive, and also 1.49, this 2y is the positive, and 10 out of 5. Right? So here comes the second nodes that covering so-called wire, 2y. We have here 4.22 from this element number 4, right? And element number 2, and element covered by element number so-called 5. Okay, so this is covered by element number 4, number 2, number 5. So that gives us another so-called stiffness matrix for 2y. Okay, 2x itself, just now, if you look into here, we have also covered this 2x. Okay, at here, 1.49. Okay, we have this 2x, u2x. You see that we have this u2x at here. All right, then we also have here is another u2x at here. So if you look into this, we have a positive, all are positive at here. 2x and 2y all are positive. Then if you look into 2x, 2y, then you have look into element number 2. Okay, then we have a positive 2 u2x. Okay, then you have here you have this negative. Okay, at here is a negative. All right, so here we have both positive. All right, then we have here negative from element number 2. This is element number 2. This is element number 5, right? So from here we have a negative from element number 2. Okay, then we have a positive 0.5, positive 0.5 for element number 5. So we have this is from element number 2, this is from element number 5. Okay, so this is from element number 5, number 2. So that built us the so-called the first two node only, first two nodes, okay, x and y, right? Then you have to go towards 3, node 3, so node 3, it will cover this one, right? Node 3 will cover by here 3x and 3y by element number 2, and as well as node 3 will be covered by this, okay, in x 4.22, element number 3. So here we have node 3, sorry, node 3 so node 3 is having here, we have node 3x, okay, we have 3x, we have 4.22, okay, then 4x is negative 4.22 from element number 3, negative 4.22, 4.22, right? Then we have also 3x and 3y covered by here, 3x and 3y covered by the element number 2, which is here, positive, so-called negative, positive, 1.49. So we have positive, okay, this is from element number 2, negative, positive, right? So that is also covered by element number 2. This is covered by element number 3. So that gives us that 3 so-called the elemental stiffness matrix that are covered by node number 3. Right? So you have to basically assemble them, okay, correctly. So if you are given all these elemental stiffness matrix, then we have to cover them, each of them, right? So this is referring to 2, this is referring to anything that related to 2 and 5. So it's all negative. So if you look into 2x and 2y, and here is 5x, 5y, all are negative at here, right? So here is given by this, right? Negative, 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 negative 0.5, which is 1.49 negative for 2x, but at 5x and 5y. So that gives us this. All right, same with here, okay, 2x, 2y, 5x, 5y, so that you have also a negative at here. Okay, so which is this one. All right, so that basically you have to be very clear on this particular thing. For example, here we have 2 and 3 is negative, positive, positive, negative. So if you look into here, the global, we have also here negative, positive, negative, positive. So same with 2 and 3 at here is negative, positive, positive, negative. All right, so that gives us what you have from this, right? These two. So we have to cover everything lah. I mean, build that the global stiffness matrix, okay, that we have built on just now. Then from there onwards, we come up with this 10 times 10 matrix of a global stiffness matrix. All right. So once we have this global stiffness matrix, then we have to, next step is insert the loads and boundaries. Okay. So if you still remember, I mean, our system, truss system is something similar like this, right? The load is applying at here. This particular point is fixed. Okay, this is 1, 2, 3, 4, 5. So 1 and 3 is 0. Okay, U1x, U1y is 0 because it's fixed. Okay, no displacement. In global displacement. Then 4 and 5, we have negative 500 pounds going down. All right. So in this case, if you after we have inserted the boundary and loads, so basically it could be further reduced our global stiffness matrix or our global matrix or solution that will be sent for solutions. So we have node 1 and node 3 is actually 0 displacement. Okay, so these 1x and 1y can be ignored. Okay, and 3x and 3y can be ignored. Okay, so end up we have 6 times 6 matrix. Okay, for our global stiffness matrix can be reduced to 6 times 6. Okay, then we have this 6 times 1, then we have this 6 times 1. Okay, and it is applying at 500, negative 500 at U4x, at node 4x, and negative 500 at 5y. Okay, so end up we have this 6 times 6, 6 times 1, 6 times 1. So if we send this to a solver, okay, here referring to MATLAB, Excel, or whatever's iterative methods, okay, then you will determine our U2x, U2y, 4x, 4y, 5x, 5y, correct? But as we know that 1x, 1y is equal to 0 because it's at the support, then 3x, 3y also equal to 0. So that gives us the so-called global displacement matrix that we have determined through this so-called global matrix equations. Okay, when we solve it, we get this. All right, so once you have solved it, you can obtain other informations, right? Post-processing part. So if sometime if we are for truss system, we are interested on the reaction force, okay, especially at the support there. So if you want to find the reaction force, So this is the equation of the formula. You want to find the reaction force of 1x, 1y, especially 3x, 3y, that is with the node. So what we do is we uh, reinsert, okay, our global stiffness matrix here is a 10 times 10 matrix, okay, we have also our U is 10 times 1 matrix, our F is 10 times 1 matrix, okay, KU minus F, that will be our reaction force. So end up, we'll find out that if we do this, undergoing this particular equation or computations, we will find out that our reaction force only happen at the support lah, which is node 1 and node so-called node 1 and node 3 in this case. Okay, so because our this is our node 1, this is our node 3, right? So here we can actually say that node 1 we have a reaction force, okay, over here is 1500 pound, and here we have a reaction force which is at here negative 1500 pound, and going up is 1000 pound. So the resultant will be some sort of this, okay, at this particular position. So that gives us additional information of reaction forces, right, of this truss system. And if we want to find the so-called normal stresses, then probably we can find our internal forces. And if you still remember, our internal forces is all local, under local coordinates, right? F equals to kx. So if I can get back our, we have the U, right? We have the global U, okay, global. So if you're undergoing this T U itself, right, then we do the transformation, make use of the relationship of global and local. We can find our U, okay. So if we can find our U of that particular members, okay, the local displacement of that particular members, then if we can find the what we call the K that we have already, that particular member, then we can find the force, okay, the force matrix, okay, the local so-called force, then we can determine our normal stress in this case, okay, F over A. Of course, we can, if you see this F over A is actually K U UIX minus UIJ also equals to AE over L UIX UIJ, then it's actually E, if you still remember, is E our strain. So our strain again is E. Here is our deformations of one particular member, delta L over L in this case. Right? So this deformation is our deformation along that particular member itself, UIX minus UJX. Okay, it's all along the X itself. So we can determine the stress also in this case. So what we do is we make use of the relationship of local and global. Okay, so to find the local displacement, we find the transpose, or what we call the inverse of the transformation metric multiplied with our U that we have. So it depends on which member that we want to actually look at lah. So if I'm looking into the element number 5, so element number 5 covering node 2 and covering node element number 5 covering node 2 and node 5, right? So we find our U we have determined this, right? U2x, U2y, U5x, U5y. Okay, so we've multiplied with this is determined, this is 45 degree. We know that is theta is 45. This is transpose, okay, T, then we can find our this local displacement, okay, of the two these nodes, okay, the local displacement, okay, of due to that particular F, okay, that gives us the local displacement X and Y, right, 45 degree. So we find U2x, U2y, U5x, U5y, right? So you can also, once you have do this multiplications, metric multiplication, you can find out that you only have 2x and 5x. U 2y is equal to 0, u 5y equal to 0. Then basically it in line with what we have assumed, right? Here in an individual member itself, the deformations is actually happen at the x-axis of the member, local x-axis of the member rather than the y-axis of the member. So you do not have any deformation in the y-axis. Okay, so if you have this, then probably we can find our so-called, if you can have this, then we can find our internal force. If you want to find the internal force, then we have this K U2x minus U5x, right? So if you want to find the stress, then we have stress equals to F over A. Then we can have this K U2x minus U5x divided by the whole A itself, okay, which is 8 squared. Okay, then we can also find the stress. So here we found that our internal force is 696 pounds, and the normal stress that develops on this particular members, which is the element number 2 is number 5 itself is 87 pounds per inch squared. All right. So that is how you manual calculates using finite element methods when you deal with truss systems. All right. So what do you think? I mean, is it very complicated when you do these transformations? Especially I think the important part is more towards the more complicated or more confusing part is more towards the what we call the assembling the global Stiffener Matrix. So you can see that now we are dealing with only 5 nodes and 6 elements truss systems, right? Then that gives us 10 times 10 matrix, and we are looking into only a plane truss systems. So if you are looking into a space truss, then you have the X, Y, and Z directions, right? So for me, it is manually. If you want to solve manually a truss system, then probably it takes some time, right? For you to for me, it's more in towards assembling. In terms of once you have assembled it correctly, okay, then probably solving you can, with the help of the computation tool like MATLAB, can help you to solve it quite accurately, right? So assembling part, you have to really take notes before you can get that final global equations correctly. Right? So if you think this is as much for this one-dimensional element systems and under truss system with orientation theta coming into play, it's very complex, okay? More very complicated to solve using FEM methods manually. So probably you can see how ANSYS solve it, okay? And you know how to formulate it already, and you know the theory behind already, fundamental behind how we formulate the problems already. So probably we can revisit these problems using ANSYS workbench and see how ANSYS solve it and how how it's solved, and also how fast it can be solved compared to you manual calculate, right? So I have this particularly my so-called workbench opens. Okay, so you know how to open your workbench. So you will see this particular layout. So we are focusing more towards on statics against then if you look into that particular problem against, right? So we have this static structure. So either you double click it or you drag it to that project schematics layout. All right. So here we go through this flow one by one. Then you can see that how the ANSYS, okay, solve this type of problems. Okay, so first we have to, because this is a wood, okay, Douglas fir wood, so we have to add a materials here. So we can always create our own materials. So you double click on, you double click on this engineering data. So in that come the engineering data interface. So we can put so here we have to put in the material properties. It's a new material, so we are putting isotropic elasticity. Double click on it, that comes this particular page. So we know that a Young modulus here is pound square inch is 1.9 E6, right? Given. And here it doesn't give you the Poisson ratios. So it's actually 0.3. We put 0.3. So that gives us the materials, right? Douglas fir that we have created, okay, manually. We define ourselves, right? Then we can close it. Then we come to the second, our third here is geometries. Okay, so if you click on this geometry, so you will see these project properties of these schematics. So if you don't see it, okay, so probably you have to go to the view here, turn it on under properties, right? So here we are dealing with line bodies, so you can check these line bodies. Right? Then in this new ANSYS, they have two modeling so-called tools. So if you right click on this, you will see design modelers and also space claim. Okay, you have two types. And my tutorials are actually using design modeler. So we will start with this. Then later on, I will show you how to model it using space claim also. Okay, so then you can try both and you can decide which one you think is easy for you. Okay, so let's try the design modelers. So what I do is I right click, okay, new design modeler geometry. So I click on this. So you'll see here the starting design modelers at here. Right, so this is the interface of what we call the design modelers. You can see also, right? So what we do, okay, we have to create so-called that particular models. Okay, so here I put in XY planes. So I will click on this. So now I'm in XY planes, right? Then I will create a sketch. Okay, click on this new sketch. Can you see that? This is a new sketch. Okay, new sketch. You click on this, then you have a sketch in XY plane. Okay. So to start with the drawing, of course, you can go to sketching here, this tab sketching, you can draw with a line, then you can set a dimension. That is another easiest way as I shown in my tutorials or the step-by-step tutorial. We use the grids. Okay, so you go to sketch, from modeling, you go to sketch, you come to setting here, then you can turn on the grids. So that give you the grids. So the grid also you have to set here. Of course, now it's in meter, the unit. So probably we have to change the unit to inch. Right? So if you go to units here, inch, so everything is in inch now, right? So here I would want to put the major is equals to 12 inch, because I want uh, each major grid is 1 feet, okay? Because for us to draw, we have 3 feet, right? So we draw it 1 feet. So the minor is also 12. So I have each. Wait, why it doesn't come up? Okay. So if you zoom in, okay, so you can see that this is my this is the scales, the legends here. So you can see that I'm zoom in, okay. So this is my minor grid. So I have 1 inch, 2 inch, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is my minor grids. Each major grid is built by this 12 minor grid, right? So it's this is from here to here is my major grid. So this major grid is basically 12 inch or equal to 1 feet. Okay, so if you zoom out a little bit, so this is 1 feet, this is 1 feet, this is 1 feet on foot. Okay, so 3 feet. If I want to draw a 3 feet, then basically from here to here, right? So with this grid, then we can go to draw a line here. So we can start from here straight away to here. Okay, we know that this is 3 feet. Then we know also it going up 3, right? 1, 2, 3 at here. Okay, 1, 2, 3 at here. Right. Then we also have this coming to here, 3. Right. Then we have from here to here, another 3. Okay. Then connecting this to here, this to here. Okay, so that gives us our so-called the line, okay, that build that particular structures. So of course you can check lah. I mean, you go to dimension, general. If you click on this line, it will tell you 50.912 is correct lah. Like what we have is three, the so-called 36 square plus 36 square, okay, square root of 36 square plus 36 square. So here is 36 inch. Here 36 inch, right? Here is 36, right? Here is 51.2 inch, right? And here is 36. So all are correct lah. So basically, if you want to double check, then you can do that, right? Okay, so we don't really need this dimension. Basically, to show you, you can cross-check your dimensions. Okay, so that gives us all the line that we have. And if you go to modeling here, okay, this sketch itself, you go to, we have to create line from the sketches. This is our sketches. So we want to create lines from sketches. So you go to concept, line from sketch, this sketch itself. So here it will give you this line. Okay. So if I click, you see that is a thunder arrow here, a symbol here. So you click generates. Okay. So hold on. So this itself is a line. Then you have a line from sketches. You have to create this, right? Then we have to go towards here to find a cross section for it. Okay, here you can put a cross sections here is 8 inch square, right? So you can put SQRT. Okay, it's 2.8284 SQ 8 inch. Right. So you can generate it. Okay. Wait, there is an error here. It should be generating the line here. I think it is not fully. Okay, so if I click on this line from sketch, okay, then we have to apply the whole thing in. So basically, it generates. So that gives us the line from this particular sketch itself lah. Okay, then under body we are having these line bodies lah. So if you see that there is line bodies, we have all these line bodies, we have the cross section. So we have to assign this cross section to this line body itself, right? So here you go to cross section, select the rectangle one that we have created just now, 8 inch square. So it generates. So that gives us our line bodies, okay, with the correct cross sections. So if you want to look into view, okay, probably cross sectional solids. So that gives us our models, right? Something similar like this. Right, so that he completed the what we call the modelings. So what we need to do is you can close it, and you can find out that the geometry wise is have a tick here. Then next you have to go towards the models. Okay, so if you double click on it, then it will lead you to mechanicals, starting mechanical in the separate windows. Right, so we wait for it to be loaded. So the model from your design modelers, it will be automatically uploaded to here. So that here you go your line bodies lah. So you can actually see it if you want in in 3D. Okay, it can be shown, but then we do not really need it. It could be a line itself, right? So what we need to do is you have to go from top down also. So the geometry, see this line body is already uploaded, which is this one. And by default, it is material, it put a structural steel. So just now we have created the material, right? So the Douglas fir boots. So we have to click on this, reassign it with Douglas fir. Right? So done. Then next will be the mesh. Right? So these meshings here, we can set the size. I mean, if you are having units inch, I mean now our units is under US customary, okay, inch. So if we set larger, so basically we are having each of this member is one element. So if you try to generate it, so here is 36 inch, here is 36 inch, right? So 36 is only 72. Here is 50.91, right? So if I put hundreds in, so meaning each of these member is one element, okay? So if you put, let's say 18, if I put 18 inch, half of the 36, right? So if I generate mesh, so you can find out that here there is one nodes, one elements, because it's 36, 18 inch. So this element itself, you have this member itself, you have two elements. Here one element, here one element. 18, 18, right? Every 18, I have one nodes or what at one nodes. So another 18, another nodes. 18, another nodes. So these are two elements, two elements. So these are also two elements, but this is 50.92. So where you can build three elements here, okay, or four nodes here. So here is one element, and one element. Same with here. So we would want to follow, because we want to revisit the problem that given in the examples, right? So we put as we can, okay? Then basically it will be similar like what you have seen in the books, right? So in the tutorials, which is one element, one element, one element, one element. So each of them is one element. Next, you see here is a question marks here. So we have to insert the what we call the loads and also the boundary or the constraint. So here is a fixed support, right? So we put at this, you see, I mean, we have to choose this node. So how to choose this node? You have to choose either this edge or the node itself. So if I choose vertex here, so then you can select the nodes at here. Okay, so you apply. So that is the first fixed support, number one. Okay, node one. Then we can add another one. Okay, add here. Fixed support at node three. Then we have to insert loads. Force. Okay, add uh, a force at the nodes. Firstly, at sorry, okay. So if I can select this first, also can, then I can put in a force applied at this particular vertex. And here you can choose to component, then you have from vector choose a component, then you know that I'm going to apply 500 pound negative, okay, going down. Then we have to create another for this particular nodes, right? Insert force, also the same. Here we have to put components negative. So that gives us all the pre-processing parts. We have completed the pre-processing part, right? So in fact we can actually start solving it. Okay, so we can click solve or click at here solve. Okay, but before we click solve, we actually can open what we want to see for post-processing. Okay, so it will help us to process everything together. Okay, so we can want to see total deformations of this entire so-called truss system, then we can put here. All right, so if you can look into solver, so in a few second time, then you can get that whole thing solved. So this is basically total deformations when you have a 500 pound at here, 500 pound at here. These 2 points is uh, fixed, right? Then that is how that deformation goes. So you can see that the deformation at, of course, the free side, the free end, when you have applied load is undergoing the largest deformations. It can go up to 0.0193x, okay? 193x so-called deformations. All right. So of course we can further to it. We go to probes. Okay. Okay. You right click inserts. Okay. We can further process it. We go to probes, deformations. Okay. So here I would want to look into this particular node. Our node here is node 5, right? So I want to look into 5x. Okay. If you can rename it, this is our 5x, right? Then I can right click, duplicate it. I want to put 5y, the same node itself. I want to look into its y direction itself. So you can evaluate all result again. Then that gives us the result of 5x, okay? And result at x-axis, in x-axis, this is in y-axis, okay? 19231, okay? 0.019231 inch. Okay, so you can compare with our calculations, I mean manual calculation, that what we get is 0.0195. Okay, compared to ours, this calculation result from N6 is 0.019231. Right, so of course you can do the same for others nodes if you want. Okay, you can go to deformations. You can go to deformations, okay? Then you can select a node at node 2. Okay, this is our node 2. Okay, I want to look into the x-axis, so that I will rename it as 2x. Then I can duplicate the same one to look into y-axis. Okay, then I will rename it as 2y. Right, then here is our 4, right? Here we can also put in insert the probes deformations. So 4x, rename, then duplicate again, and we have rename 4y. Here we have to change to y-axis. So we can go evaluate all result. We don't need to solve it already because it has been solved. This is more towards post-processing. Okay, so we can evaluate it. So this is our 2x, 2y, okay, 4x and 4y. Then you can compare actually with your calculations results. All right. So of course, after this, you still remember just now our example, we look into the reaction force. So here also you can refer to the reaction force I had here. You go to probes, okay, force reactions. You click on force reactions, then the fixed support, which is this one, is our node 1. Then you can also come again here, choose the node 2, node 3. Okay, then you can evaluate it. So you can find out that what just now we have is around 1500 for node 1, right? Going this direction, this is around 1477.1. So the reason behind there is some y force reactions, it is because of this NC's solution y is using iterative methods, right? And also the model wise, okay, what we have calculated just now is mainly a translational x and y directions. So here, of course, it consider the rotation part. Okay, even it's a plane, but then it consider the rotation part. That is why you have the moments. Okay, when you have applied a force at here, you have the moments. Then you have additional rotation here. That is why you have a slightly different force reaction result, 1477 compared to 1500. So in for this particular direction, so the same, negative 1500, we have negative 1477, and we have 1000 in 1000 pound in y directions. Here is 985. Right. So of course you can look into the internal force also, like what we have. You can go to beam result axial force. So this axial force is what you have here is our so-called internals. Okay, so if you see this, this is so-called our internal force lah. I mean that we have just now calculated for element number so-called 5 just now. From element number 5 just now, we have the internal force is at around 696, right? 696 pound. So if I can put in approach, okay, at here, so you can see that it is quite close lah. It's around 700 somethings. Okay, so this is 700 something. This is maximums at here is 1367. This is also in compressions. Once 477 is larger than this in tensions, then we have this member is around 512. This member is around 500. This member is around 482. Okay, so that is so-called our internal force. So if I can use this result and divide by my areas, 8-inch square, right, then it will give us the stress. Okay, for this line element, it doesn't give stress, but what you can do is we can create a so-called user defined results. Right. So what we can do is we can find hold on, let me show you. What we can do is we can insert that, or you can find from here lah. If you see here, open. Okay, then available solution quantities. So these are the expressions that you can actually use. If I want to find the rotations, okay, is there any rotation coming in? Rx, Ry, Rz. Of course, Rx, Ry, it will be 0 because it will be a rotation along the about the Z axis, right? So it's Rz. So if we want to create this, we want to look into this also can. So you can see that there is a what it means. Oh, here you haven't. We have to choose this. Okay, equals to, we can insert the what we call the expressions for this particular case. The axial force divided by 8, or what we call the internal force divided by 8. Then you can actually use these particular expressions. Hold on, let me type it out for you. All right, it should be beams. You can write what you can do is you can write here under this one, you can write beam 188 fx, right? Then we divide by the area itself. Here is 8 lah, 8-inch square. Okay, so everything we divide by 8 itself, then it will actually, we don't need to put equals here. So that gives us the what we call the stress. Okay, so if you go evaluates, right? So that is our stress. So just now our stress for element number 5 is 87. So if I can put a probe at here, so it's around 88 right? So that is all the value of our internal force that we have obtained here. Okay, internal force divided by 8, that you will get this result, right? So the rotation wise, when I said got rotation, that is because of the moments. So you will have a so-called rotation about the z-axis. So that is why you have some result difference between your case manual calculations and as well as the when we compare with the ANSYS, right? So that's it. I mean, you can make use of the expressions, okay, to determine a user-defined results, right? Or you can make use of whatever that you have here, okay? Whatever that you have here, then you can actually also determine the results, okay, from here. So if you come back to this project schematics, so you will see that all are completed. So then you have all ticks at here from engineering data up to the results. Okay. So that give you the what we call the results, right? So you can compare and you can actually know why there is some difference when it happened to ANSYS and Workbench. Okay. So manual calculations is there, okay, you can use it, of course, but then it involves the transformations and involve the compilation of your Stiffness Matrix. So that will be slightly sometimes will become confusing, okay. But then in this particular case, ANSYS will help you to solve. So what you need to do is modeling and set up the correct settings, okay, inserting the correct initial settings. So what will affect the results? This is again is an approximation. What will affect the result is again if you look into the project schematics again, I would say it will be under your materials, right? You key in the raw material properties, you affect your geometry that you have drawn, okay? You have model, if you are inch, you put a meter, then probably everything will go wrong. Your model, under model here, your mesh, okay? If you key in the correct very small mesh, you will get a better result, but it will take longer times, right? Then the fixed support, the constraint and the load that you apply, okay? So these are all giving you what we call the material that you assign, right? All will basically affecting or contributing to the deviation of the result from the actuals. All right. So that is about these problems. Okay. Then probably I can show you how to model in another software. Okay, another tools. Okay, which is Space Claim. So let me a quick one before we end these sessions. So again, under here, you click line bodies, then you go here, right click, you open new Space Claim. All right. So here you will see starting Space Claim at here on the bottom left. So we just wait for another while, it opens. So you will totally different interface, but in terms of modeling, will be quite similar. Again, we are looking into XY plane. So what we need to do is we put XY, right? Then we go to File. Okay, we change the units. So we go to Space Claim Options. Click on it. File Space Claim Options. Coming to the units here, we change to imperials, right? So everything in inch. The grid itself, we also make use of the grids. The minor will be 1 inch. Okay, the line for one majors is per major is 12. So basically, one major grid will be 12-inch or what we call 1 foot. Okay, so we click OK. So we need to call out the grids. Okay, so what we need to do is we click on this. Okay, so we click the grid itself. So that we create just now the new sketch planes. Okay, which is XY plane now. Then we click on the grid itself. Then here it comes the grids. So you will see that we zoom in. Each major grid, this is major grid. So each major grid I have a 12-inch, okay, of minor grid. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this itself is 1 foot or 12-inch. Okay, so now I can start drawings. So what to start drawing, so you have to click under this sketch modes, okay, under design, sketch modes, then you have to click the line here. So from here, okay, click, then easily you can draw lah. So this is 24-inch, I want 36, so I can type 36 straight. Right, then you can go up vertically, another 36. Right, and I can go here 36. Right, then I can draw another new line from here, 36, and I can connect them. 50, you see that it show 50.912. Okay, and here 50.912. So all are correct. All right, so here we go. It gives us line 1, 2, 3, 4, 5, 6. Okay, so this is our line that built these particular things. Next, we have to we have to create the areas. Okay, here is a square cross-sectional area. So you go to prepare, okay, profile. You can click on the profile itself, and you have a rectangle. Okay, so if you can click on this rectangle, okay, then edit beam profile. Then here you can edit your so-called dimensions lah. So just now we have a cert 8, right? Is 2.8284. So we put 2.8, right? Then another one, click on this, 2.8284. Enter. So now basically it gives us the radius, the dimensions for this particular is 2.8284. So what we need to do is we have to go back to design. Okay, here is design under structures, right? So we have to assign all these line to this rectangle. So what we need to do is under design, we go to select, okay, select all these line using shift, okay, select shift this, all these 6 lines, 1, 2, 3, 4, 5, 6 line, right? You go to prepare, and you create, click this create. Right, so you will see that now all the line become beams. Okay, beam rectangle. So what we need to do is also go back to design, then we go to select. Okay, so from here to here we want to compile it as a so-called combine them as a one so-called structures. So what we need to do is we select, okay, select all, okay, using shift, then right click, move to a new component. So make it as a one components, right? So this will become our one components here, right? So here we put merge them all together so that complete our so-called models, right? So if I can close it, then you see a tick here. Then we can double click on this. Then it will start mechanical again. All right. So you will repeat, basically you will export import your model from the space claimer geometry here. So you just wait for it to import. Then you repeat, yeah, that comes your models. Okay, if I want to show in 3D, that is the same models lah, right? So what we need to do is repeat what I have mentioned to you just now, or I've shown to you just now. So here, material, you have to change to, just now I didn't add, you have to change to the correct models, correct materials. Then the mesh, right? Then the inserts, the supports, as well as the force. Then you can solve it, right? Or you can insert some post-process result before you solve it, right? So that is how you model it using a space claimer for these particular models, right?